Hey everyone, and welcome back to my science studio. In our last lesson, we talked about single displacement, also called single replacement reactions, which followed this general formula, where we have A reacting with BC to produce AC and B. And if you remember, only one element replaces another here. If you haven't done so already, I highly recommend you check out my lesson on single displacement reactions, because today we're going to be learning a new reaction called double displacement reactions, where essentially we're going to be adding one more letter to that formula. We're going to be adding a D. And so instead of one replacement, now we have a double swap. So let's get started. In a double displacement reaction, two ionic compounds react by exchanging their cations. Remember, an ionic compound is a bond between a metal and a nonmetal. And a cation is a positive charge, and this is usually indicative of metals. So here we have a general formula that says AB reacts with CD to produce AD and CB. So here in this formula, our A and our C are your cations, your positive ions, and they swap partners. So instead of A staying with B, it's going to pair with D, and C pairs with B. That's a double displacement. We're having a double switch. And just one thing to note before moving on, keep in mind that your B and your D are your anions, your negative charges. Okay? Now, there are a few types of double displacement reactions, but the main one we'll be focusing on today is a precipitation reaction. There are also gas formation reactions and acid-base reactions, which, don't worry, I will talk about in another lesson. Now, unlike single displacement reactions, we do not really use the activity series here. Instead, we'll be learning how to use a water solubility table, which gives us a set of rules. And these rules help us predict whether a compound is soluble in water or not. In other words, whether or not it will dissolve. And by the way, these rules are also super helpful for single replacement reactions too, which I promise we'll do practice problems on single replacement reactions in another video, so don't worry. But anyways, this table is not something you're expected to memorize. Your teacher or your professor will give it to you. The goal is not memorization, but understanding how to read it. And honestly, if you want my opinion, I tell my students this all the time. The more you practice and the more you use it, the more comfortable it becomes. So let's talk some symbols. You see, if something is soluble, like I said earlier, it dissolves in water. And we label it aqueous or AQ. If something's insoluble, it does not dissolve in water. And so instead of writing aqueous, we now label it as a solid or S. And you see, a precipitate is simply a solid that forms in a reaction. So a precipitation reaction is a type of double displacement reaction, where essentially you start with two aqueous substances and one of the products forms a solid. And that solid is your precipitate. So keep that in mind as we go through our examples together. So let's go ahead and walk through the first example step by step. Our first reaction says that lead 2 nitrate, or PbNO3 reacts with potassium iodide, or Ki. Now, both reactants are aqueous, meaning they dissolve in water. And first, we want to identify the type of reaction. Of course, this lesson is a double displacement lesson, so we expect a double displacement reaction, but let's see why. Remember the pattern AB reacts with CD to produce AD and CB? Well, here we have our A, that's our Pb2+. Our B is our nitrate ion, our NO3 with a -1 charge. Our C is our potassium, which is K+, and our D is iodide, or I with a -1 charge. So if you notice, I went ahead and uncrossed all the charges in order to identify my A, my B, my C, and my D. Keep in mind that our B is a polyatomic ion. It's the nitrate ion. And like I said in a previous video, try to keep them grouped together as one unit. Because this is a double displacement reaction, the cations, the positive charges, they swap partners. So they're going to swap anions. So let's look at the right side. Without crossing the charges, let's just pair them up. So our A is our Pb2+, and that's going to pair with our D, which is I with a -1 charge. When we cross the charges, we end up getting Pb, I2. And that's going to react with Cb. Our C is K+, and our B is NO3-. Crossing the plus and the minus charge, we end up getting KNO3, or potassium nitrate. So our unbalanced products are lead-2 iodide, right, PbI2, and KNO3, potassium nitrate. Now we got to balance, right? We have to fulfill the law of conservation of mass, which says that matter cannot be created or destroyed. It can only be conserved. Again, I like to keep polyatomic ions grouped together. So if you saw my lesson on balancing chemical reactions, you know exactly what I'm talking about. But if you prefer to split the polyatomic, so the nitrate in this case, into N and O, and then count the atoms separately like that, go for it. That's all on you. I just prefer to do a little bit less math. So here we go. Now, going ahead and balancing, let's count our atoms first. On the left side, we have 1 Pb, 2 nitrates. Remember, that 2 outside of this parentheses tells me that I have 2 nitrate ions present here. If you choose to split the N and the O, you could say that you have 2 times the amount of oxygen, which is 6, because 2 times 3 is 6, and 2 times the amount of nitrogen, because 2 times 1N is 2. So you could do it like that, but because I like to keep polyatomic ions grouped together, I'm going to just write a 2 here because that's how many nitrate ions I have. I have also 1 K and 1 I. On the right side, I have 1 Pb, 1 NO3, 1 K, and 2 I's. Now, I noticed the nitrates first. Why? Because I need 2 of them on the right side because I have 2 already on the left side. So if I place a 2 in front of KNO3 as a coefficient, now that 2 distributes to the NO3 and now I have 2 nitrates present. But whenever you add a coefficient, always ask yourself if you changed anything else. And you did. You changed the number of potassiums because now I have 2 Ks. So in order to balance the potassiums on the right with the left, if you add a coefficient of 2 in front of the potassium iodide, or the Ki, now I have 2 potassiums. And luckily, by adding a 2 as a coefficient in front of this compound, now our iodines are balanced. We have 2 on the reactant side and 2 on the product side. So this should be our final balanced equation. Now that we're balanced, we can go ahead and predict the solubility of our products. And to do so, we have to use a solubility table. I highly encourage you to use the table that your teacher or professor gives you in class because that's the one you'll be seeing on your exam. But for now, we can go ahead and use mine. And what I recommend you to do is just take it step by step, okay? If it takes you longer to get to the answer, that's totally okay. It comes with practice. So let's look at this, PbI2. And we want to see whether or not it's soluble or insoluble in water. And the first rule that just immediately draws my attention is rule number 4, where it says that all chloride, bromide, and iodide ions are soluble. So technically this would have been aqueous, right? Because that's what it means to be soluble. But there's an exception. They say that yes, it's soluble, except when it's bound to silver, lead, or mercury salts. And the lead here specifically has a +2 charge, which is exactly the charge of ours. So it's not soluble. It's not aqueous, so we have to write the solid symbol. Looking at the next one, potassium nitrate, I immediately am drawn to number 3, where it says that all salts containing the anions, and they mention the NO3 negative ion, the nitrate ion. They say it's soluble, and there's no exception here. That means it is soluble, and we have to write the aqueous symbol. And that's that. That's our final balanced equation with the correct states of matter. Okay, now I urge you to try this next problem, where a student mixes solutions of ammonium nitrate and potassium sulfate, and they ask you to predict the products and explain why no visible reaction occurs despite ion exchange. Go ahead, pause the video, and when you're ready, play and we'll go through it together. Okay, the first thing you're going to do is you're going to write your reactants, and they give it to you. They give you NH4NO3, and that's going to react with K2SO4, potassium sulfate. Write the arrow, because you're trying to see what it produces. You're predicting the products. And right off the bat, I recognize this as a double replacement, where I have my A is my ammonium ion, my B is my nitrate, my C is my potassium, and my D is my sulfate. So now that we have the ions, now we can pair up. Our AD, right? Our A is going to be ammonium, and our D is our sulfate. When we cross the charges, we get NH4 in parentheses with a 2 on the outside, SO4. Remember, that 2 came from the sulfate. You have to write the parentheses around the ammonium to tell the person that you have 2 ammonium ions present. Okay? And that's going to react with our CB. Remember, you always write the metal first. It's not BC, it's CB. The C is your metal. This is an ionic bond. It's metal and non-metal. Metal is written first. But anyways, so our C is our K+, and our B is NO3 with a -1 charge. So when we cross the plus and the minus charge, we end up getting KNO3, or potassium nitrate. Now let's go ahead and balance. On the left side, on the reactant side, we have 1 ammonium, 1 nitrate, 2 potassiums, and 1 sulfate. On the right side, we have 2 ammoniums. Again, if you wish to split the polyatomic, this is like saying 2 times the amount of hydrogen, 2 times 4 is 8, and 2 times the amount of nitrogen, which is 2. But we're just going to keep it as 2 ammoniums here for simplicity. We have 1 sulfate, 1 potassium, and 1 nitrate. Now, the first thing I look at is the fact that I have 1 ammonium on the left and 2 on the right. So if I put a 2 as a coefficient on the left side in front of the ammonium nitrate, now I have 2 ammoniums present. But that also changes the number of nitrates. So now on the left, I have 2 nitrate ions. In order to balance the nitrate ions with the right, we have to add a coefficient of 2 in front of the KNO3 on the right side. But that also changes the number of potassiums, which now we have 2. Which, luckily for us, on the left, we also have 2 potassiums, so we're balanced. And the sulfates are also balanced here. We have a 1 and a 1. Fantastic. Now let's go ahead and use our solubility rules to predict our solubility of our reactants and our products. So on the left, we have ammonium nitrate. And rule 2 says that all ammonium salts are soluble, meaning you write the aqueous symbol. K2SO4. Rule number 5 says that all sulfate ions are soluble, except when bound to any of these 3 ions. This is not lead or strontium or barium, it's potassium. So it's not an exception to the rule. It's soluble, so we write aqueous. Now the products. Ammonium sulfate. Well, this is just like rules 2 and 5, actually, right? All ammonium salts are soluble, and number 5 says that all sulfate ions are soluble, except with those 3 exceptions. And this is not one of those 3 exceptions, so guess what? It's aqueous. And the last product is our potassium nitrate. Rule number 3 again says that all salts containing the anions, like nitrate, are soluble. So we're going to write the aqueous symbol. And this is our final balanced equation with the correct states of matter. And if you notice, everything is aqueous here. So even though ion exchange occurred, in other words, we did do a double swap, no visible reaction happens because no precipitate was formed, or gas, or water for that matter. That's why this is considered no visible reaction, even though it's technically a double replacement. Thank you guys so much for watching. If this lesson helped you at all, please don't forget to like and subscribe to my channel. In my next lesson, we'll be doing a full practice problem set where we mix single and double displacement reactions, where you will be identifying the type, predict the products, and apply your solubility rules and your activity series. So definitely check that out. But in the meantime, happy studying.